colleagues, friends, fellow Earthlings, and explorers who wish to see the ocean depths near and far. Welcome to Ask An Astrobiologist, the show that celebrates the science and the scientists involved in our quest to understand the nature of life. I'm your host, Dr. Graham Lau, also known online as the Cosmobiologist, and of course, we're brought to you by the NASA Astrobiology Program and SaganNet.org. As always, a huge thank you to all of you who tune in for our show, who are watching right now live and asking questions in the chat and having conversations about our theme of this month. And a huge thanks to all of you out there who watch the show afterwards and leave comments for us to come back and check out, and who interact online with myself and our guests and NASA Astrobiology. We appreciate all of you so much. This month, a huge shout out to our ambassador of the month, the PCE3 user on X. PCE3 is one of the research coordination networks of NASA Astrobiology. It stands for Prebiotic Chemistry in Early Earth Environments. So a huge thanks to them for sharing about the show and getting involved. Now, today's episode is going to feature Dr. Richard Camilli, a scientist from Woods Hole Oceanographic Institution, and you just saw a trailer for the most recent episode of Our Alien Earth. We're going to dive into that episode and its theme a little bit today during the show with Dr. Camilli. Dr. Camilli started off studying biology before getting into engineering and received his doctorate from MIT in 2003. His work focuses on developing and using autonomous robotic systems for things like oceanography, space exploration, disaster response, even subsea archaeology, which is pretty cool. So welcome, Dr. Camilli, and thank you for joining us for Ask an Astrobiologist.
Thank you for having me. It's a pleasure to be here.
Well, I'm so glad we can have you join us to talk, one, about this recent episode of Our Alien Earth, but also to share about your career and your research interest, and to talk about things related to astrobiology. Now, with all of my guests, I like to start off just knowing what your science origin story was. What got you interested, for instance, in your case, to study oceanography and robotics and pursue this career?
Okay, well, we'd have to go back a ways. When I was a kid, I really wanted to be a paleontologist, and I still enjoy collecting fossils, going to Museum of Natural History in New York. And I guess over time that evolved into studying biology, and did my undergraduate work in biology. I almost went to med school, but based on some advice from friends, they suggested that I consider engineering because I like to build things. And so that's what I did. And then went on to become an oceanographer. And now a lot of my work has kind of come full circle there. And so there certainly is a biological component in terms of being able to develop robotic environmental sensors, and also for looking for and characterizing life forms in the deep ocean, and potentially developing technologies that can be used for spaceflight systems to do the same.
Very cool. Now, early on in your career, you made the switch from biology as an undergraduate to doing graduate school in engineering, which I've met a lot of people who've gone the other direction, but very rarely from biology to engineering. Was that a difficult challenge for you in your educational career to go to an engineering field after doing biology?
It did require kind of doubling up on some of the coursework, shifting gears a bit. But I have to say that it was exciting and fun. And if I had to do it all over again, I would.
I love that. Yeah, for myself, I went from biology, chemistry, and astrophysics and jumped into geology, even though I only had 3 undergrad courses in geology before grad school. So I think it's good for everyone who wants to be an astrobiologist to know there are lots of different directions you can take. Now, I'm curious, before we speak about the research you've done in Santorini and this recent episode of Our Alien Earth, how have you seen the field of oceanography changing during your career, especially relevant to your research?
One of the things that I've seen during my career is a shift in terms of technologically what's possible. And maybe a way to sum that up is that early on with field robotics, the technology was very limited, and so we tended to operate robotic systems in fairly controlled environments. And now with the sort of acceleration of technologies and capabilities, we're now using robotic systems for operations in places that are not only difficult, but also potentially dangerous. And we're using these robots in areas that where we couldn't send humans.
Very cool. And I'd love to explore that then with this recent episode of Our Alien Earth and the research you've been doing off the coast of Santorini. Now, these pools that you found, I think originally in 2012 from the episode, they're called Callisti limnes. First off, can you explain what that word means, that term means, and what these pools, why they're significant?
Yeah, so I guess maybe we can preface this by saying that scientifically, whenever you discover something, you get to name it. And so my colleagues and I named this geologic phenomenon Callisti limnes, and the name stems from ancient Greek, Callisti meaning most beautiful, and limnes meaning lakes. And so the Callisti limnes, they have this really cool characteristic that when you view them from inside a submersible, they have this iridescent sheen to them, just like an opal. And as a matter of fact, the material that makes up these lakes or pools is 10% by weight opal, and so they're kind of jewel-like.
Oh, very cool. So what drew you to exploring this region in the first place, I guess, is a big question.
I got involved with that project because of some colleagues over in Greece who had been contacted by the Greek government because Santorini is an island that is also sitting on top of a caldera. As a matter of fact, the island is the rim of the caldera, and it's back in 2011, the caldera started to become active again with what are called seismic swarms, lots of earthquakes, and the entire island started to inflate. So there was they put together a team to investigate this and to prepare for potentially having to evacuate people from the island. And the reason for that is back about 3,500 years ago, the volcano erupted during the Bronze Age, and it destroyed an entire civilization. And so we didn't want a repeat of that, so we wanted to be prepared. So the team was assembled to go and investigate, and I was invited to join on the team, and so that's how we started there, and that's how we found these Callisti limnes.
Wow, it's incredible. Like connecting ancient history to modern disaster understanding and preparing for possible impacts, and then connecting to deep sea observations of geology and biology that connects to astrobiology. I love seeing all those connections. And for you yourself, a lot of your work is focused on autonomous robotics, things like the gliders that anyone who watches that episode will see being deployed underwater. What are the biggest challenges for you for deploying autonomous robots that go and explore underwater?
One of the biggest challenges, one of the kind of the major focal points of my research group's work is perception. And basically, for a robotic system to be able to perceive its environment correctly and then make appropriate decisions so that it can complete its mission. And humans are excellent in terms of their perception abilities. Robots, not so much. And so we're trying to improve that.
Very cool. And I imagine it's getting better. We see a lot of things in robotics getting better all the time on the land and in the ocean. You said in the show that deploying the gliders in this specific site was like hang gliding in Midtown Manhattan at night. Why is that? Why is it the case these gliders had so many obstacles to overcome?
So I guess I'll use a technical term here. The gliders are what we, in engineering parlance, consider underactuated. And in other words, they don't have a lot of power to control themselves. to position themselves. The gliders, the reason that they don't have that kind of power is because power requires energy, and these vehicles are designed to carry out long-term reconnaissance. And so long range, that means that they have to be energy efficient. And so anyway, by being energy efficient, they have to have very, very low power draw, roughly the same as a cell phone, to operate a robot. And so they use the environmental energy, draw some of that environmental energy to help them move along. But again, they can't just kind of parallel park themselves if they find something or do these sorts of things. So that's a big challenge. The other one is perception. Robots are easily fooled, so figuring out ways that they can explore an unknown environment and keep themselves relatively safe while collecting the useful information to hand back for another robot to complete its mission.
Very cool. Now, one thing that popped out to me, being a huge fan of Star Trek, when I watched the episode of Our Alien Earth about Greece, was that you have these algorithms for deploying the robots named after Star Trek characters, Kirk and Spock. And so, you mentioned earlier you were interested in paleontology when you were young. It's not surprising, I think. Most of our folks we've had on the show are interested in paleontology and space. There's a big connection there, but a lot have also been fans of science fiction. So are you a fan of Star Trek and science fiction? And has that kind of inspired your own career and the things you think about?
Yeah, definitely. As a matter of fact, oftentimes on expeditions, we'll make reference to specific episodes and particular lines from Star Trek. But I should say that the Star Trek characters that are that some of these algorithms are named after, that's the work of my colleague Brian Williams at MIT. He is a big Trekkie, and each of those the named algorithms, let's call them, their characteristics are somehow linked to the characters in Star Trek.
Very cool. So I want to speak just briefly about our connections then to all of Earth's oceans, as well as to other oceans elsewhere. So first off, how does this research in deploying these robots in this specific location off the coast of Santorini, how does it better help us understand geology and biology of Earth's oceans globally?
Well, certainly that area is around Santorini and the Colombo volcano. You could think of that operationally as kind of a crucible in terms of the challenges that they present for these robotic systems, which is kind of a proving ground. If they can operate there, they can operate in many other places. So that's from kind of the engineering perspective. From the scientific perspective, certainly the observations that we make, for example, around Santorini, do have very important implications for understanding the Earth, the ocean, climate cycles, etc. And one case and example is going back to the Callisti limnes. The mechanism that causes those to form, we have evidence to believe is a process wherein the carbon dioxide dissolved in the water makes it heavy and causes it to pool. That has very important implications for some techniques that are being considered right now, sometimes referred to as carbon capture and storage, where the idea is to instead of allowing carbon dioxide from combustion emissions to go into the atmosphere, is to just inject them into the deep ocean. The idea being that the ocean is vast, it should dissolve and disperse. But in this case, we see a phenomenon that wasn't considered previously, that the carbon dioxide will actually settle to the bottom and create these this pooling effect.
It's incredible. So I love that connection to the Earth's climate and carbon dioxide and carbon capture. I was in Iceland this summer and saw a really cool place where they're capturing carbon dioxide and trying to create rock out of it. But there's obviously many different formats for doing carbon capture and trying to have some impact on the world's carbon budget right now. And so that's really cool. Do you think, and so if it's speculation for fun, like long term, if we did start injecting that carbon dioxide, do you think at such depths we could have similar systems forming away from volcanically active, more shallow regions? Do you think that the same kind of systems might form, or do you think it'd be like wildly different seafloor settings?
There are very specific conditions that would have to be present for that, but it's conceivable that you could have these things forming elsewhere in the world, certainly.
Very cool. So it's an astrobiology show, and so we have to talk a lot about space exploration and trying to better understand not just life here on Earth, but the possibility for life elsewhere. And so I wonder, from your viewpoint, how does your research deploying autonomous robots for various regions around our planet in Earth's ocean, how does it apply to exploring oceans of other worlds like Europa or Enceladus?
Okay. Well, right now the scientific hypothesis, kind of a consensus really right now, is that Europa and Enceladus contain liquid oceans underneath an ice covering, which is not unlike the polar ice caps in the Arctic and the Antarctic ice shelves. They may be quite a bit deeper on these, or thicker on these other planetary bodies, but developing the technologies that can go and study under ice is something that for here on Earth is a big deal in itself. But again, it becomes sort of a proving ground for developing these technologies for exploration under Europa or Enceladus ice cover. And
fantastic. And then the ice cover is one thing to think about. So we asked our audience before the show with one of our polls on YouTube through NASA Astrobiology what the biggest challenges might be for us in future missions to put robots under that ice and to explore for life on Europa. We gave people options like building autonomy for our robotic explorers to be that far away from the surface, finding a way through the ice itself, communicating information back to Earth, and then also a big one, withstanding Jupiter's radiation belt. Of those possible answers that we gave, we also allowed people the option of making some comments, but the biggest that people selected was finding a way through that thick, icy crust. Now, on Earth, we don't have any ice anywhere on Earth that's remotely as thick as what we think Europa's ice is. So we have to figure out how to get down through that first. Do you have a perspective on the importance of getting through the ice and how we can deploy robots below the ice through things like Nereid, which was used in this episode of Our Alien Earth, or other robotic missions in the future?
Yeah, so getting through the ice is daunting, and there are several groups that are focused on that, and it'll be interesting to see which of the different techniques really kind of wins out here. There are techniques that are currently used, for example, to bore through the ice sheets in Antarctica. Typically, you're talking about hundreds of meters of depth that they have to bore through. But in terms of we could talk about the specific designs of that, but I think for purposes of my work, the big implication is that the larger a diameter that you have to bore through, the more energy it takes. So that translates into, if you're going to make a robot, you want to make it as small as possible. So you have to only make a small hole in the ice. And so that really puts an emphasis, again, on sort of these accommodation factors like low power, small form factor, the ability to operate without lots of actuators and things like that, getting back to that under-actuated aspect. And then for the communications, that's really hard because anytime you go under ice or underwater, it's opaque to most of the electromagnetic spectrum, radio waves, light, etc. And so communications becomes incredibly difficult. And from a standpoint of autonomy, that has huge ramifications. The autonomous systems that we put underwater or under ice have to be truly autonomous. We don't talk to them until they return to the surface, and so they have to find their way. They have to have that sort of the cognitive abilities, the perception to be able to complete their mission and come home.
Very interesting. And I love this idea of having like a smaller diameter borehole. Do you think in the future we might like to deploy like huge fleets of very, very small micro robots into oceans on Earth or other worlds?
I could see there are some advantages to redundancy, and but there are some trade-offs as well. One thing is if you make a system smaller, hydrodynamically, the fluid that you operate in, the feeling of it changes. So if you think about like something like a plankton, a little tiny organism that's swimming in our oceans, to that organism, seawater feels like honey. It feels super viscous, and that's why they move slowly. Whereas a bigger organism like a shark can move much faster. So there's a trade-off in terms of the coverage rate, if you will, and the size of the vehicle, the number of vehicles, et cetera.
Very cool. I mean, it's still just fun to think about what the future of robotics in our ocean and Europa's ocean and other worlds might hold. Assuming we can get through the ice, there are lots of techniques that people have suggested, things like using a nuclear engine to melt through the ice and various methods of boring. Our best estimate right now is that the ice in Europa is some 10 kilometers thick, which is, extremely thick. So, communication between a fleet or even a single robot will be extremely difficult, but there's so much cool stuff going on right now across the solar system, on our own planet, and exploring oceans. I wonder if you can give us the bigger vision that you have for, let's start off just with Earth exploration. Where do you see the exploration of Earth's oceans going, let's say the next decade?
One of the big things that we are focusing on is sort of the event response. So there are phenomena that occur on Earth, like say, for example, a hurricane, that if you want to be able to make measurements of, say, like the energy transfer of a hurricane, you have to be right there, right then. And when I say you want a sensor there, you don't want a human there. And so it means having a way for robotic systems to be able to, on a moment's notice, start a new mission, arrive on site very quickly, and then respond to the environmental dynamics. And that's one thing that we're working on quite a bit in oceanography, so that we can have a better kind of observation capability of the Earth. 70% of it's covered in water. And if we were to compare the sort of the weather stations underwater with those on land, they're incredibly sparse. And there's an interesting tie-in if you look at how meteorologists collect their data. A lot of that data was collected, or the ability to collect the data comes from airports. So aircraft need to have information in order to plan their routings and so forth. And so that's why that system was created. We don't have that quite yet underwater, but the technology that we have to build for that, because we don't have the advantages of radio links and so forth, makes it more closely resemble what we would need for planetary exploration, particularly under ice.
That's incredible. I guess just for fun, for a follow-on of that, do you think we'll be sending humans more underwater and building like underwater habitats, or, on the ocean surface, like more cities and things like that in the future? Or do you think the real future of oceanography does lie in robotics?
From the, if you think in terms of the infrastructure that's required for humans to live underwater in habitats, it becomes more challenging. In engineering, we call that a hotel function. Literally, all of the infrastructure that's required to support that thing, that agent, person, could be a robot, by the way, but robots take a lot less care and feeding than humans. And I have spent quite a bit of time underwater. When I was younger, I was a saturation diver, and I can tell you that it's very the work underwater physiologically. It's hard for your body, and you have these issues of fatigue that set in that can really change a person's ability to operate. And so the nice thing with robots is they tend not to get tired. They do break, but they tend not to get tired or need sleep.
Yeah, it's pretty incredible. I mean, I think a lot of us interested in space exploration and the astronautics and astrobiology are also scuba divers and have been underwater. I've never done deep water diving myself, but I do remember reading the book The Last Dive and just being blown away by some of this technical diving that people have done. And it is very dangerous. It has led to some accidents and injuries and things like that. So that's always an important part, I think, for people to remember, whether we're sending humans down into the deep ocean or off to other worlds like Mars or beyond, is there are a lot of impacts for putting humans into environments that we just didn't evolve to live in. It's a huge impact. Now, I'm curious, you mentioned connections of your research to climate, to disaster, and how disasters can unfold. You have a lot of things going on. Your research has touched on archaeology and a lot of other realms. How do you see these connections all playing together through oceanography and through your work to the future of things like space science, biology, or maybe even philosophy?
Oh, wow. That's a big question. In terms of the connections, one thing that's emerging, or it's becoming more and more apparent, is the linkage. One of the things that my group focuses on is what we call shared autonomy or collaborative autonomy, and that's human-robot interaction. And this is something that you see on the International Space Station, where there are robotic arms and stuff, continual maintenance on the space station. But you see that playing out also with the various Mars landers, where there are humans back on Earth that are directing robots on Mars, and the ability to for that to function smoothly is a complex process, and we can certainly design robots that are able to complete a task. Like, think about robots on a factory floor where they're in this controlled environment. The humans give them a directive and put yellow tape around the robot, and the humans don't go into that space. The robot does its job. With the human-robot interaction, this is where you have to have the humans and robots interacting in terms of understanding intent between, let's say, an autonomous system and a human-directed command. It goes back to kind of Isaac Asimov's principles, right? Anyway, one of the things that's emerging is trying to better understand human cognition. And, these issues like, for example, let's say from one human to another, they could have different skill levels. And for a robot to be able to understand those differences and choose to function differently based on the human that's there, and things like, for example, fatigue or attention, to understand when a human's not paying attention. It basically boils down to issues of trust. And we think about humans trusting robots, but the converse can be true as well, where the humans or the robots have to understand the nuances of how to trust humans so that keeps the humans safe. So this is something that it really moves over into kind of the brain and cognitive science aspects, and also the general philosophy of how we understand our world.
Yeah, it's incredible. And I love that connection of like, how we build autonomy into robots and give them some kind of thought, on top of their sensing, like how can they actually use an intelligent process to have some sensing of what we're going through and what they're actually doing in the work along with us humans. There definitely is a very interesting future for autonomy and robotics, for AI, and for what we humans have in exploration. Now, I have a couple more of my own questions before we jump to our faster than light segment. But first off, in prep for this episode, you told us about a recent sighting you had of a cool columnar feature underwater. It's kind of like seeing Devil's Tower below the ocean. And we're just wondering if you could explain that for our audience so we can talk about it a little bit.
Okay, so this goes back to the Colombo expedition that we did as a part of the NASA P-STAR program, and we were examining the inside the caldera of this volcano, the Colombo volcano. It's one of the most active and most dangerous volcanoes in that part of the world, and the best way that I could describe the inside of the volcano is for the folks out there that are fans of the Lord of the Rings trilogy. This is like descending down into Mordor. It is an active volcano with hydrothermal venting. They're basically underwater fumaroles. Plenty of sulfur to go around. If you could smell underwater, it would probably smell pretty bad. But anyway, one of the things that we saw with our initial sonar reconnaissance, we used sonar to map the inside of the volcano, similar to the way that for the orbiters, the way that orbiters will use radar to map the surface of, say, Mars or Europa. And anyway, with the what we call digital elevation maps that came back, there were these spires that just went straight up. And think of, again, back to the Lord of the Rings, these towers. When we looked at them, we thought, well, that's probably the hydrothermal venting, and it's probably gas bubbles rising up from these volcanic vents. And so we thought, all right, let's go check that out. And so we sent in the vehicles, and one in particular, the Nereid under ice vehicle. And when we got there, the pilots were extremely tense because it turned out that it wasn't fluids rising up from these vents. It was columnar lava, very similar to the Devil's Tower, and these were just going straight up. And the amazing thing, we want to get back to kind of astrobiology, because of the way that the volcano is structured and the various volcanic fluids coming out, like the carbon dioxide, for example, and sulfur and all of these fluids that come out of the volcano. If you look at these spires, they're several hundred feet tall, basically vertical, and down at the bottom, the environment is very similar to what we think the prebiotic Earth was like before life existed, before we had an oxidizing atmosphere. And as you ascend along the spire, it's like stepping forward in time again to where we get to our modern ocean. And so it was totally unexpected that we would find these things. We're looking at the life forms as we went along, and found some interesting organisms. One we call a lollipop sponge. It looks kind of like a lollipop. And sponges are kind of unique organisms because in terms of their biochemistry, they have a lot of tricks up their sleeves. And, if you think about humans, we have two biochemical pathways we can use: aerobic and anaerobic. We prefer to use the aerobic approach, but occasionally we have to resort to anaerobic respiration. Sponges have at least another one up their sleeve where they can use nitrogen, and so it confers an advantage to them. And anyway, so there are these different life forms that are using little biochemical tricks to make a living in areas where we couldn't, and it's interesting to see that. And it gives kind of a map of how life may exist other places in our solar system, other places in the universe, by using these biochemical pathways that give them a little bit more of a thermodynamic advantage, let's say.
I love that. Yeah, there's so many cool things that life on Earth does that helps us to better understand what we're looking for out there. Possible metabolisms, biosignatures, things that are left by life that we could look for. It's all extremely intriguing. So thank you very much for that. I do have two more of my own questions here. One, so we have people who watch the show who are maybe early career scientists, or maybe younger people who they want to know if like a career in the field of astrobiology or oceanography or robotics is right for them. What advice would you give to someone who maybe wants to follow in your footsteps, or at least achieve some similar research goals as you have?
Well, I'd say number one key ingredient is follow your curiosity. I mean, science is curiosity driven. I mean, that's how we come up with hypotheses. That's how we come up with ways to test these hypotheses. So, yeah, without curiosity, you really can't move forward. But if there's something that you really are interested in and have curiosity, it's certainly I would pursue that myself. And that's what I've tried to do in my career.
Heck yeah, I love that. And then finally, what legacy do you hope to leave in the fields of oceanography and robotics?
I'd say, just kind of abstracting back, the legacy that of my work is that I hope to advance our scientific understanding by creating technologies that allow us to observe the previously unobservable. And so, a lot of my work focuses on developing the tools so that we can observe something that was otherwise invisible to us. And that kind of eureka moment of when you do see something, that's just the kind of the ultimate reward, and that's the kind of legacy that I would like to leave.
It's fantastic. It sounds like a good legacy. Now we're going to do our faster than light segment. So just some kind of easy questions. We ask these of all of our guests just to kind of get an understanding of what different astrobiologists and researchers around the world think. So first and foremost, we mentioned science fiction earlier and Star Trek. What stories have inspired you to want to learn more about life in the universe?
I have to say, one of the stories that really kind of was formative for me was a biography it was given to me. It was a used book. It was given to me when I was a kid. It's a biography of a deep sea diver named John Johnstone. And as a little bit of background, he was a diver. Was born in the late 19th century, and he was one of the deepest divers at that time. And he wrote about things that he had seen. And one of the jobs that he had was at one point fixing a communications cable between Tasmania and Australia. And he walked something like 40 or 50 kilometers on the seafloor and just observed the world around him. It was kind of mind-blowing. I got the book when I was like 8 years old. It was like, wow, all this stuff. So yeah, that book kind kind of brought my career full circle into oceanography.
Wow, that's so far to walk underwater. That's so cool. It's like walking in like an alien environment, like one of the Apollo astronauts or something.
Yeah, and as a matter of fact, that there's the Aquarius habitat off Florida. I spent a while there. You live underwater for weeks at a time, and that habitat is used to train astronauts for spacewalks and that kind of thing. So yeah, very, very similar.
Yeah, absolutely. Now let's shift gears. If you could go back to the beginning of your career, what advice would you give yourself?
Wow. That's a challenging one. I think I would look at, particularly in my studies, at some of the different subjects that, the hindsight's 2020. Now I can say, yeah, that I like, for example, cognitive science. That's something that had I to do it all over again, I'd go back and take a couple classes on that at least, and maybe devote more of my studies to that. But yeah.
Interesting. So we have another question I'm going to jump to then, because it's kind of interesting. So say you could choose a different career. If you could restart your career today, what would you study?
May study a little bit more of archaeology. I mean, I've done a few expeditions, underwater archaeology, and we tend to underestimate what humanity was capable of in ancient times, and certainly we really underestimate their capabilities prehistorically. And so I would probably study more about that. I mean, one thing that I find fascinating is with the new developments in using DNA to reconstruct the past. For example, putting together the genome of the Neanderthals and understanding them, who they were, just from the fossil evidence. That's something that, yeah, I'd love to learn more about.
Yeah, absolutely. Life has done so many cool things on Earth. Humans have done so many cool things for us to explore and learn more about, and we have more ahead of us too. So let's think more about life then in general. What is your favorite thing that life on Earth does?
Kind of going back to the issue of the sponges having that trick up their sleeves biochemically, living systems find a way to make a living. And if you think about life, it's this unbroken thread that we trace back through our ancestors, and every life form can as well. And, we tend to think of life as fragile, but it's really robust. I mean, genetically, humans and bananas share about 50% of their DNA, but we're so different. We're using the same kind of building blocks and can come up with and life has come up with all of these creative solutions for operating and living in environments and finding ways to coexist, with the symbiosis and, even just plants and animals being kind of the yin and yang for products and reactants. And so, I think that's really amazing. And to be able to maintain that, it's kind of creating order from disorder, using the sun's energy to do that, or the chemicals deep in the earth to do it.
Yeah, fantastic. And we have a lot of similarities and some differences. And so that goes into our next question. If you could communicate with any non-human organism on Earth, what would it be and what would you want to talk about?
I'll digress for a moment on that one. Some years ago, I was in Alvin on a deep dive, and we were out in the Eastern Pacific, not too far from Los Angeles, maybe about 1,000 feet down. And normally, when you do these dives, when you're transiting between study sites, you try to conserve power. You turn off the lights and that kind of thing. And anyway, we arrived at this one site, turned on the lights, and there were some fairly large fish swimming around on the bottom. And all of a sudden, this a group or swarm of jumbo squid just showed up out of the darkness. And these are Humboldt squid. They're 5 to 10 feet long, probably bigger than an average human. And they are very, very aggressive. And they were swooping in and just grabbing these fish and chowing down. And they communicate with each other. They seem to hunt in packs. So they have kind of a society. Anyway, at a certain point, one of them swam up to the sub and started feeling around with its tentacles. And I had my face in the viewport, and it swam up and put its eye right up there to look inside. I mean, it's clear it was curious, and maybe it was hungry too, but I'm glad that there was some titanium between us. But at the same time, it's clear that, these organisms have a society of sorts. They communicate with each other. They use a very different method for communication. They communicate with their chromatophores on their bodies. So they change colors. But yeah, if I could talk with an organism, I'd be interested in finding out, its thoughts on the world. In particular, think about its origin story. I mean, do squid consider where their origin is? They only live a year or two. So anyway, that would be one organism that I'd be interested in finding out more about.
It's so cool. Yeah, there's so many cool creatures out there on our planet. And yeah, there's so much non-human intelligence for us to learn more about and maybe one day have those conversations. So I have one more question in our Faster Than Light segment, and then we'll jump to our audience Q&A so that folks who are watching live right now can ask questions of you in the chat right now on YouTube. My last question. What is an unbelievable science fact that still blows your mind?
Oh, that one's easy. That we are made of star stuff, to quote Carl Sagan. When I found that out as a kid, I used to watch Cosmos, and that still just blows my mind that, we're made out of materials that were formed in a supernova, that we have no idea where, when, how. I mean, maybe the how, but that we were made of that. It really just kind of expands my idea of the vastness of the universe.
It's beautiful. Yeah, we certainly are the cosmos coming to know itself, which is pretty incredible. Now, for those who are watching live, you can ask questions in the chat if you like. I have some questions already here. So I'll start off with one from Andrew Rowan, who reached out to me in particular on Facebook. Just curious what you think of the best environments for exploration, specifically whether we should focus on something like Enceladus, which has a much thinner icy crust, even though it's a smaller ocean, than someplace like Europa.
Europa certainly has its challenges, and the other, along with the ice, also the radiation field. I would be happy with either one. I'd say Enceladus, maybe a kind of a personal favorite, but that's just because of personal preferences.
Very cool. Let's say we do find alien life out there on Europa or Enceladus or Mars or an asteroid or an exoplanet. Jim Pass reached out on X and wants to know what you think would happen to humankind, to our societies, should we find alien life, and should we specifically find a second genesis of alien life?
Wow. I think it would certainly change the conversation in terms of how we view ourselves. and hopefully it would make us a little bit more attuned to the value and the beauty of life here on Earth. I mean, who knows what that xenobiotic kind of organism is, or I guess xenoorganism. I wonder how much it looked like anything here on Earth. Is it carbon based or not? Yeah, I think it would just change our view of who we are and where we are.
Yeah, I agree entirely. And we just don't know long-term implications societally. That's why people like Jim Pass himself, who is a sociologist, are important in that work. Now, the user rendering reality 3D animations on YouTube who's watching live wants to know what you think of including hydrophones or microphones on underwater robots to listen for alien life, say on Europa, or techno-signatures, like signs of technology out there. And I'll even add to that, just using hydrophones, microphones here on Earth to better understand the sounds of our oceans.
Certainly, we use hydrophones quite a bit. And as a matter of fact, it's one of the techniques that we use for conservation methods for cetaceans, whales. There are a number of whale species that are critically endangered, and we use those here on Earth to help protect those whales. For exploration, absolutely. I mean, the hydrophones are a great way to be able to detect, in particular, seismic activity. We could do that. That would tell us a lot about, for example, Enceladus and Europa. Certainly, biologically, underwater acoustics is one of the preferred modes of communication for organisms.
Absolutely. And just to add to that, do you think when it comes to ocean exploration and specifically things like the cruise ship industry, the shipping industry, do you think that we humans owe it to ocean life, maybe more specifically marine mammals, to consider the sounds that we're putting out into the ocean? And if so, how could we best approach that issue?
Certainly, the environmental noise is becoming a greater and greater issue. Fortunately, there are organizations within, for example, the shipping industry that have been working toward minimizing acoustic disturbance. And another thing that has been gaining momentum is using these other vessels, let's say non-scientific vessels, as platforms of opportunity to put sensing systems on to help, for example, protect whales. I have a colleague, Dan Zitterbart, who's developed a advanced kind of imaging system that can operate 24/7 on ships to identify, for example, whales, and let the crew know that whales are present so that they can reduce their speed and minimize the disturbance.
Yeah, very cool. We have another question concerning contamination relevant to your study sites, but I think first I'm going to ask this question by Lucas Lee, who just kind of simply wants to know what programming languages are you using for autonomous technology on your robots?
The preferred, if we want to go super low power, we always try and go with the compiled language. Sometimes we get down to just regular machine code. If we're doing something that we want to send out for extended periods, we'll use that. We'll use C, C++. When we're doing development work, we tend to use interpreted languages like Python, for example.
Very cool. And then, so jumping back to contamination, Anurup Mohanty, who's one of our production assistants, wants to ask his own question. He wonders what your thoughts are on the future of deep ocean tourism and whether you're concerned about contamination for study sites that we're trying to understand scientifically.
The deep ocean, maybe I should. One of the things that is an issue with the deep ocean is that there's already been quite a bit of contamination, in the sense that the ocean, it's like a highway that's been without an Adopt a Highway program for thousands of years. And so, I mean, that's why archaeologically it's interesting to find shipwrecks, but at the same time, we have all kinds of debris that just gets dispersed into the ocean. I've done 60 some expeditions in my career, and I have yet to visit any part in the deep ocean where I have not found trash or litter from humans. Oftentimes, quite a bit of plastic.
I mean, that really speaks to whether or not we currently are in an Anthropocene, given our impacts geologically, biologically, atmospherically on all of Earth's environments. We humans are making a large impact, whether we want to really discuss it or not. It's out there, and we don't know yet the long-term ramifications of those behaviors. Which also, for me, as an astrobiologist, speaks a lot to our questions of alien civilizations and whether they've gone through these periods as well, where they had to realize what they were doing. But I do love that kind of idea of this being a highway without a highway adoption program in the oceans, and that a lot of our long-term trash throwing behaviors has ended up in the oceans. So we have one last question from our audience. Lucas Lee wants to know what your biggest gripes are with the way that either astrobiology or oceanography have been portrayed in fiction.
I'd say for a lot of fiction, I'm thinking of sort of like Hollywood movies. Oftentimes they portray the people in these domains as kind of cowboys, and it's kind of superficial. And I think that if we look at the kind of the union of the two, that there's, particularly with the exploration, there's all kinds of history that's untapped that would make just for interesting stories. Like, for example, each of the space shuttles was named after an oceanographic ship. As a matter of fact, the Atlantis, my favorite, because the Woods Hole Oceanographic, Atlantis was its first ship. And so these expeditions of discovery are key for both space and oceanography. And I think maybe that's why we all like Star Trek, because it does have a little bit deeper storyline.
I love that. There's some great, cool tie-ins to science fiction and to what we share and the stories that we tell. I think you're right about the kind of cowboy behavior, things like Armageddon and Deep Impact and those kinds of things. There's also great things like The Abyss. I thought James Cameron's The Abyss back in the 80s was a really interesting exploration of what it could look like. So I think we are at the top of the hour and the end of our episode. So Richard, thank you so much for joining us for Ask an Astrobiologist. And to everyone out there tuning in, you can reach out to all of us online and find us in the various places we are. But one big thing, if you want to learn more about Dr. Richard Camilli's research, you can go watch episode 3 of Our Alien Earth on NASA Plus, as well as the NASA Astrobiology YouTube channel. More episodes will be coming out, exploring field sites all around the world and various astrobiology teams who are working and asking questions of how we can explore the Earth to better explore for life out there. So for all of you tuning in, we super appreciate all of you. You are a fantastic audience. Dr. Camilli, thank you so much for joining us. To everyone out there, thanks for joining. And until next time, stay curious.